Hello everyone, welcome back. Today I'm going to explain a problem on design of shear, that is module 4 of PSC. An unsymmetrical I-section bridge girder has the following sectional properties. Area of the cross section 777 into 10 power 3 mm square. Second moment of area 22 into 10 power 10 mm power 4. Width and thickness of the top flange 1200 into 360 mm. Thickness of the web 240 mm. The centroid of the section is located at 580 mm from the top. The girder is used over a span of 40 meter. The tendons with a cross section of 700 mm square are parabolic with an eccentricity of 1220 mm at the center of the span and 0 at the supports. The effective pre-stress in the wires is 800 Newton per mm square. If the tensile strength of concrete is 4.5 Newton per mm square, estimate the ultimate shear resistance of the section. Assume failure to take place when the principal tensile stress reaches a value equal to the tensile strength of the concrete. Overall depth is equal to 2000 mm. So in the question, these are the data given. First of all, the data is it's a unsymmetrical I section. It is having an area of 777 into 10 power 3 mm square. Second moment of area 22 into 10 power 10 mm power 4, and width and thickness of the flange is 1200 into 360 mm. Here you should keep one thing in mind. They have said it as I section, unsymmetrical I section, but they are not giving any information about the bottom flange. We have the information about the top flange, so it is 1200 is a width, the thickness is 360 mm. Thickness of the web is 240 mm. Centroid of the section is located at 580 mm from the top. This word is important. It is centroid is measured from the top. It is at a distance of 580 mm. Length of the girder is 40 meter. The cross section of the tendon is 70 mm square. It is having a eccentricity of 1220 mm at the center of the span and 0 at the supports. At the center, eccentricity is 1220 mm. At the supports, it is 0. Effective pre-stress in the wires is 800 Newton per mm square. This is tensile strength. They have given about the overall depth. They have clearly mentioned to estimate the ultimate shear resistance of the section. Okay, so this ultimate shear resistance should be found out. See, according to the data given in the question, I have just drawn a unsymmetrical I section. You can see here top flange is greater than the bottom flange, as I don't know anything about or no dimension about the bottom flange, so I'm assuming that the top flange will be length will be more compared to the bottom one. So I have just written like this. This red dot is nothing but centroid of this I section, unsymmetrical I section. Where the centroid of the I section lies means that is here. This green color is centroid. Okay, first I will explain about these things. Next is about the centroidal distance. In question itself, they have given from the top it is 580 mm. So from here up to this neutral axis, it is 580 mm. They have given about the area of the cable and all. So eccentricity at the center is 1220 mm is at the center. Here we have a cable. From the center of the cable to the center of the neutral axis or centroid. Okay, both are same. The distance between these two is eccentricity. E is equal to 1220 mm is a eccentricity. So write a measurement like this: 1220 mm and 580 mm is a centroid distance from the top, and overall depth they have given it as 2000 mm. First, while solving a problem, we should write down the data, and while writing, be careful. They have mentioned it as top. So y top is equal to 580 mm. These are the remaining data. Whatever I have explained, I have mentioned it here. Now we require the pre-stressing force. So generally the formula, or not generally, it's a standard formula: pre-stressing force is equal to initial stress into area of the cable. What is the initial stress? It is 800 into area of the cable. I'm talking about the cable. So it is 700 mm square. If you multiply, you will get P is equal to 560 kilo Newton is a pre-stressing force. Next is, see here, we should find out sin theta, FCP term and all. Why do we require that? We have a VCO, that is ultimate shear resistance of a section. For ultimate shear resistance of the section, the formula is VCO is equal to 0.67 B into D into whole root of FT square plus 0.8 FCP into FT plus P sin theta. This is a formula. So we know that already we have B value, D value, FT also is known, but FCP is not known, as well as sin theta. These two terms are not known, so we should focus about that point, that is to find out these terms. So get back here. BW is equal to 240 mm. FCP formula is P by A, that is load by area. How much load they have given? It is 560 into 10 power 3 whole divided by, it is area of the section, 777 into 10 power 3 is equal to 0.72 Newton per mm square is a FCP value. Next is sin theta is equal to 4E by L. This formula is used when it is a parabola with concentric. On that condition, we can use this formula. E value is known, that is eccentricity at the center is 1220. Take that into 4 whole divided by 40 into 10 power 3, that is length was in meter, convert that it into mm. You will get sin theta as 0.122 is a sin theta. So get back to the formula, substitute all the terms. About the B, be careful, we should substitute the width of the web. So 0.61 into 240 into 2000 into whole root of FT is, in question itself they have given FT value. So FT is 4.5 square plus 0.8 into FCP is 0.72 into 4.5 is a FT value, plus P value is 560 into 10 power 3 into sin theta is 0.122 is a value. Therefore, we will get PCO, or ultimate shear resistance of a section, has 1605.35 kilonewton is a value. So this is how we will calculate VCO formulas or VCO values. Hope you have understood. Thank you.